Every mistake is a lesson, and every lesson is a stepping stone towards becoming stronger, wiser, and more compassionate person. Your worth is not measured by your failures, but by your ability to learn, grow, and continue moving forward. Once you recognize your worth, it becomes easier to set. And now let's get started to fix the solutions for today's problem on group theory. And this is related to MFCS, DMS, and DMGT, and also for the BSc students. Now the problems are, we have to show that the set which is of the form A plus B root 2, where A and B belongs to Q, is an abelian group with respect to addition. So here is the set, and we have to show that this is an abelian group, and the binary operator here is addition. And the second question here is, show that the set Z comma 0 is an abelian group where the circle is an operation defined by A circle B is equal to A plus B plus 1. This is Z comma circle is an abelian group. We have to show that this set is an abelian group where circle is a binary operation and it is defined as A circle B is equal to A plus B plus 1. And now let's get started for the first solution here. I am selecting the set here. See here, the first question here is, show that the set A plus B root 2, where A plus B belongs to Q, is an abelian group with respect to addition. So we have to show that this is an abelian group. The binary operator here is addition. And now I have considered this set as Q root 2, which is of the form A plus B root 2, where A and B belongs to Q. First, in order to show it's an abelian group, we have to prove 5 properties. One is closure, associativity, identity, inverse, and commutative law. And the first thing is associative law. So this is, first one is the closure law. So I am taking two elements from the same set, that is X, which is of the form A1 plus B1 root 2, and next Y from the set Q root 2, which is of the form A2 plus B root 2. Here the binary operator is addition, and therefore I am adding these two, that is X plus Y. If I add these two terms, see here A1 plus A2. If A1 is a rational number and A2 is a rational number, addition is also a rational number. So this can be written as B1 plus B2 into root 2. So which is of the form. So if you consider this as a single element, this will be of A3 plus B3 root 3, which will be in the set Q root 2. Q root 2. And therefore, if you observe this one, X I have taken from Q root 2, Y I have taken from Q root 2, and the addition X plus Y also belongs to Q root 2, and therefore Q root 2 is closed under addition. Clear? And the next one, we have to prove associative law. For associative law, we have to consider 3 elements, that is X, Y, and Z. So after considering X and Y, now I have considered X plus Y plus Z. See here, I have added these two, and next one Z I have added. So after addition, so A1 plus A2, and next one B1 plus B2 into root 2. So if I bring this A3 also, this will be of the form A1 plus A2 plus A3, and here also B1 plus B2 plus B3 into root 2. So if I interchange this one, as these are the rational numbers, so rational numbers satisfies the associative law. I have interchanged the brackets here, and therefore this can be written as A1 plus B root 2 one side, and next one A2 plus A3 plus B2 plus B3 root 2 at one side. So this can be written as X plus Y plus Z. So after taking X plus Y plus Z, so we got X plus Y plus Z, and therefore X plus Y plus Z is equal to, see here, X plus, this is Y plus Z, which is nothing but an associative law. Therefore Q root 2 is associative. So I have shown that it is closure, it is associativity, and next one is identity law. So for addition, 0 will be the identity element. So 0 belongs to Q root 2, and which is of the form 0 plus 0 root 2, which belongs to Q root 2. And therefore if I consider, so if I consider X plus 0, so if I add this X with 0, then what happens here? So X is nothing but A1 plus B1 root 2, and 0 is nothing but 0 plus 0 2 root 2. So if I add these two terms, that is A1 plus 0, and this for next time, that is B1 plus 0, again this will be X, and therefore we got, see here, X plus 0 value as X. and therefore we can write this as x plus 0 is equal to x is equal to 0 plus x, and therefore 0 will be the identity element in q root 2. Therefore q root 2 satisfies the identity law. And next one is inverse law. For inverse, so we know that for a, additive inverse is minus a. See here, I have taken x as a1 plus b1 root 2, which belongs to q root 2, and here minus x will be minus a1 minus b1 root 2, which also belongs to q root 2. So here is an addition between x plus minus x. So after addition, see here, I can write this as a1 minus a1 plus b1 minus b1 into root 2, which is equal to 0 plus root 2, which is equal to again 0. So this is 0, and therefore if you observe this one, x plus minus x is equal to 0 is equal to minus x plus x, and therefore minus x is an additive inverse of x, and therefore q root 2 has an inverse element. So 0 is an identity element and minus x is an inverse additive inverse of x, and therefore it satisfies the inverse law. And the last property here is commutative law. For commutative law we have to take two elements, that is x plus y. So here x plus y I have considered this value can be written as a1 plus a2 plus b1 plus b2 into root 2, as a1 a2 are rationals and it satisfies the commutative law. I can interchange. I wrote this as a2 plus a1 plus b2 plus b1 into root 2, and this can be written as a2 plus b2 root 2 plus a1 plus b1 root 2, which is equal to y plus x. This is y plus x, and therefore q root 2 is a commutative law. Q root 2 satisfies the commutative law. So I have shown that. So here x belongs to, see here, x belongs to q root 2, y belongs to q root 2, and x plus y belongs to q root 2, and therefore it satisfies closure law. And for associative law, see here, this is x plus y plus z is equal to x plus y plus z, and therefore q root 2 is associativity. And next one is identity law. For any addition, 0 will be the identity element. I have considered x plus 0 is equal to x, which is equal to 0 plus x, and 0 is the identity element. And next one for inverse, as you know that for a, minus a will be the additive inverse. Therefore x plus of minus x is equal to 0, which is equal to minus x plus x, and therefore q root 2 has an inverse element. For the commutative law, x plus y is equal to y plus x, which is commutative. So all the properties, that is closure, associativity, identity, inverse and commutative law holds, and therefore we say that q root 2 is an abelian group with respect to the binary operation, that is addition. And here is the next question here. What is the next question? The next question, or the second question here, is z comma 0 is an abelian group, and 0 is an operation defined by a circle b is equal to a plus b plus 1, and now we have to show that it is an abelian group. Here z comma 0 is given, and we have to show that it's an abelian group, and here circle is a binary operator with which is defined as a circle b is equal to a plus b plus 1. So here is the solution. So it is given that very clear statement that a circle b is given that a plus b plus 1, and first we have to check with closure law. In order to show it is an abelian group, the first property here is the closure law. So here a plus b is a set of integers. So here if you consider this one, so a belongs to, see here, a is an integer, b is also an integer, implies the addition is also an integer. Clear? So if you add up 1, so that is also an integer. So what if a plus b plus 1? So a plus b plus 1 is nothing but a circle b, which belongs to z, and therefore we say that a belongs to z, b belongs to integer, and therefore a circle b belongs to, so belongs to z, and therefore G is closed under circle. Therefore G is closed. Therefore G is closed under the binary operation circle. And the next one is associative law. For associative law we have to take three elements. For associative law I am considering three elements. So now I consider A circle, that is B circle C. See here, this can be written as, it is B circle C. So this can be written as, for, see here, A circle B, it is defined as, A circle B is defined as, we have to add these two for one time and we have to add one for one time. So now I am adding these two, that is B plus C and again plus 1 according to the circle. definition. See here, again there is a circle operator here, and now we have to add these two terms, and again we have to add 1. That is, if you consider this whole as a one part, this is a plus b plus 1, and this is nothing but a plus b plus c plus 2. So make it as a 1 here. So this is nothing but a circle. So this is nothing but a circle, b circle, c. And now we consider a circle, b circle, c this time. So for a circle b, what will be the definition here? That is a plus b plus 1. This is a circle C. So if you consider these two as different parts, this is A. The whole thing is A plus B plus 1. So which is equal to, this is A plus B plus C plus 2. And this is the second one. So if you observe, both the answers are same. That is A plus B plus C plus 2. And this is A plus B plus C plus 2. So this value is nothing but A circle B circle C. And therefore, from 1 and 2, A circle, B circle, C value is nothing but A circle, B circle, C. This is from equation 1 and 2. If A circle, B circle, C is equal to A circle, B circle, C, A circle, B circle, C, and therefore we say that G satisfies. So here Z satisfies associative law. Associative law. Under circle. So under the binary operator, circle. So here it is not G, it is Z. Z is closed under circle. And next one, after closure associativity. So we have identity law. So we have identity law. So for identity law, as you know that, see, every time you know that A circle E is equal to A, which is equal to E circle A. And now this time also I am considering A circle E is equal to A. So what will be the identity element? So according to the circle definition, so we have defined A circle B value as, so we have to add A plus B plus 1. And here also the same case I am adding these two, that is A plus E plus 1, which is equal to A. So if I cancel these two, A plus 1 is equal to 0 and E is equal to 1 minus 1. Therefore, E is equal to minus 1 is the identity element. Is the identity element. So for this set, we got an identity element. And the next thing here is inverse law. So for inverse law, what is the condition here? That is A circle B is equal to E is equal to B circle A. For every A comma B belongs to Z, then B is the inverse of A if this property holds. So as defined, A circle B is equal to A. So we have to add these two for one time and again add 1. So this is E. What is our E value here? So E is an identity element which is equal to minus 1. So I am substituting minus 1 here. That is A plus B plus 1 is equal to minus 1. And therefore I need B value here. As B is the inverse of A, I need the inverse element. And therefore I am sending these two to other side. This is minus 1 already. This is minus 1 and this is minus A. So B is nothing but minus A minus 2. And therefore B is the inverse of A. Therefore every element has an inverse. Therefore Z has, B is the inverse of A. Therefore every element has an inverse. Therefore Z has inverse element. Z satisfies the inverse law, or Z has an inverse element. And the next one is commutative law. For the commutative law, so every time we show that A circle, consider A circle B. So for A circle B here, we have to add these two. For A circle B, what we will do? We have to add these two plus 1. And again I am interchanging, that is B plus A plus 1. So which is equal to B circle A. And I have considered A circle B, and which is equal to B circle A. Therefore, A circle B is equal to B circle A. For every A comma B belongs to Z. and therefore Z is commutative. Z is commutative. So after satisfying all the properties, we clearly say that Z comma 0. Therefore, Z comma 0 is an abelian group. Is an abelian group. See, let me explain you once again. First thing is closure property. So have shown you A belongs to Z, B belongs to Z implies A circle, B belongs to Z. Therefore, Z is closed in a circle. For associative law, I have shown that A circle, B circle, C is equal to A circle, B circle, C, and Z satisfies the associative law. And next one is an identity law. So according to our definition, A circle E is equal to A, and therefore E is equal to minus 1 is an identity element. And for the inverse law, so B is an inverse of C. B is an inverse of A. We are getting the identity element. We got the identity element minus from, and therefore after substituting, B value is equal to minus A minus 2, and B is the inverse of A, and therefore Z has an inverse element. And next one is commutative law. So if you consider A circle B, we got B circle A. If A circle B is equal to B circle A, Z is commutative. So it satisfied. Z satisfied closure law, associativity, identity, inverse, and commutative law. If all the 5 properties holds, then we say that Z circle is an abelian group with respect to circle, and therefore, so it is very easy to solve. If you follow these videos, it will be very helpful to show it's an abelian group or a commutative group. If you really understand, you know what to do, please raise your thumb, pass it on to your friends, and subscribe to this channel and stay connected. And I'll be uploading so many theorems, so many problems related to these series, and definitely it will be helpful. And all the videos are downloaded in the playlist. Please go through the playlist once and check all the topics which are needed for you, and it will be very helpful for your preparation, and you can get a good score. Thank you so much for watching and staying till the end.